Hi guys, welcome to the first video on my channel. Today we are looking at the Rietveld refinement of lead sulphate or PbSO4. It is an important material to study because lead sulphate crystals can actually form when lead batteries start to degrade. This tutorial will follow the input files from TOPAS version 7. They can be found in the manual section of the application files. The starting model that we are going to use is from the ICSD code that is listed on screen. We're going to work through how to set up your own input files using TOPAS and Notepad. I use Notepad just because it makes it easier. And then we'll use some Fourier difference maps as guides to which atoms and positions need to change, as well as some of the thermal displacement. The first part will consist of Pauli refinement. We will extract the unit cell parameters, and then from that we can focus back on the atomic positions. So here is the XRD pattern for lead sulphate, and the first step in any refinement is to fit a background function. You can see from the background on the scan it is flat, no humps or rises. This would be good to fit with a Chebyshev polynomial, a low order polynomial, but I will show you a different method which can be good for more experimental data. Okay, so now I'm going to open GSAS 2 and I'll show you how to extract the background. So insert the XID pattern and click through the instrument files. Now you see the pattern is there. Then you click background, compute auto background, and then I always use the improve function with a log lambda of 7. You just click define the fixed background, and that will save it as a separate file from the scan. Then we're going to export it. So we'll export as a Topaz XIE file and save that as background. It will save in the same file. Okay, so let's set up our Pauli refinement input file. We're going to insert the R factors, and then we're going to put a line underneath that. The apostrophes are included so that these lines don't actually contribute to any of the refinement steps. Now I have input the instrument parameters. So now we're going to add the background function and 1 and x and 0 error. These are all required as part of the refinement. We're going to set the background so that it is what we chose from GSAS. The parameter S controls the scale of the background, and fit objective applies. The last thing I've added is a HKLIS phase with the phase name as PbSO4, included the space group from the ICSD code and the lattice parameters from the ICSD code. I've also included the crystallite size Lorentzian and the strain Lorentzian as well. Okay, so I think we're ready for
a polar refinement. I just want to add that I included this line so that the Rietveld refinement will stop at 102 theta. And these are for the peak shape and contribute to the peak shape. Okay, so we want to save this file as a .input file, or else Topaz won't let us run it. So we can go to Topaz now, let's launch, get the input file, here's the input file, and then we just click play on the launch mode kernel. And here we go. So first time around, I would generally press no. So if you press yes, it's going to update your input file, whereas it makes an output file. So I'm going to click no. We'll go onto the file. So you can see it's made an output file as well now. So it's got all of the reflections, and then it's got the refined values of A, B, and C. So now that we've done this, we're gonna run it again, and it will be the same, but we'll click yes this time, and this will update the input file. So now the input file has updated with the refined values of A, B, and C, crystallite size and strain, and we've got the values of the 0 error, 1 and X, and the parameter S. So we're going to use this file, and we're going to copy the input file and duplicate it. Okay, so then we'll rename this, because this is going to be our Rietveld input file. So we'll call this one now. We'll open it. It's going to be the same as the input file, and we're going to delete HKLIS, and we're going to delete load HKL, because we don't need this. Okay, and now we're going to import the atomic positions, and we're going to put scale factor on the atomic positions as well. So let's start by calling this now structure, and we've got let's put these together. Now we're going to include the atomic positions, and they must be in this syntax or else it won't let you run the refinement. So the @ symbols mean this value is being refined. And so I'm going to delete all of these @ symbols, and I'm going to change the atomic positions to be what it is in the ICSD file. Okay, so I've now changed all of the atomic positions and the thermal displacement parameters to that of the PNMA PbSO4 phase on ICSD. I've also changed the input file so that it outputs a CIF, because we're going to go on Vesta and view the structure as we refine it. So let's go and take it over to Topaz and see what it gives us. I forgot to add, we need to include a scale, or else you'll end up with an XID pattern that is quite intense. We're also going to uncomment all of these, I did just run the poly again with that uncommented, and it shows that the RWP for the poly was 8.8, so that's what we're aiming towards with the Rietveld refinement. So now that we're ready to take the Rietveld refinement into TOPAS, we're going to save it, so Control S. And then we're going to load the input file, the Rietveld, and run it. Okay, so we got an RWP of 10.771, which is not bad. We're going to click no for now, just because we're going to keep the input file as it was when we started it, so we can change things slowly and see how it updates. So we'll click no, and we'll open that output file instead. So the next thing I'm going to do is start to look at the atoms. So for this, I'm going to fit all of the parameters we have assigned already, except from the scale. We'll keep the scale on. And then we're going to start with the heaviest atoms first. We'll start with the lead, because you want to get your heaviest atoms found first, and then it will sort of lower the amount of error in the lighter atoms, such as the oxygen. Another thing we're going to add onto here is the difference Fourier map. We can just place that in there. And then remember to save again. And this time we might refine, let's refine the positions of the, actually first of all, let's show you the Fourier map. So if we save this and run this, interesting, it didn't open. Okay, I'll fix this 1 minute. Easy mistake to make. So I was editing the output file instead of the input file. This happens a lot. So we'll paste that in again, and we'll take off these. And leave the scale on. Or we might keep it at 0.03. And now we'll start this. Actually, we might change this as well. Let's change these and just do this. Makes it quicker. And we'll show you what the Fourier map is like. So here is the Fourier map. You can see that the electron densities are in the right position. we can see everything's in the right sorted place. But so I'm looking for any sort of points where I think the positions might change. We're going to refine all of the positions we can anyways. But okay, so now we can go back and start changing some of the positions. So if I set that this position is locked by symmetry, so we can't change that one. We can change these two, and then we'll save that and see what that looks like. We make this a bit smaller. We'll bring it down here. So the RWP was 11. Now 11.12 down. Let's see what it looks like in the output file. So 187 is 1879 more or less. 16732, which is not bad. So we'll run that again, and we'll probably accept that. Now we can come back to the input file and let's. Oh, we didn't have the scale on. Let's do that again. One 187. Yeah, that's fine. We'll run it again, and then we'll accept it. Now, please. And now we will look at these filters. You know what, we might keep these two on. Save that, and then run the refinement. So the RWP went down again. So we will, before we accept or reject that, let's check it. 16732, 785, 143, 0.434, that's fine. 0.18546, that's fine as well. Okay, so we'll accept that as well. So I'm checking to make sure the positions aren't going too out of where I know they should be. If they do, then something's going really wrong. It shouldn't. If you follow a SIF and your material is what you think it should be, then the deviations from the SIF file should not be a lot. So now we've found the heavy atoms, I'm going to lock the positions of the X and Z in these two, and now we'll have a look at the oxygen. So this Y value is locked by symmetry. So this Y value is locked by symmetry. This one is not. So we can refine these, and we'll see what it's like with them all refined. If we have to do it one by one, we can, but let's see what it looks like after this. So the RWP went RWP 101, 102. It didn't really change. Let's have a look at the positions. I think I was doing it in the wrong file again. Let's do this. Let's put these in again. This happens so much. And save that. And I improved the RWP by quite a bit. Have a look at the thing. It looks a lot better. I was looking at these oxygens. Let's do this. Okay, this looks okay. Let's get the positions. So 5-9 to 5-9-6, that's okay. 9-5, that's fine. V1, that's changed by a bit. So we'll just keep our eye on this one. And 0.037, that's okay. 4-2, that's fine. 9-7, that's okay. 3-1, that's okay as well. So it's just this one. 3-1, just changed by a little bit, but not too much. So we'll accept that. And we will then, what I like to do actually, before I go into the thermal displacement, let's unlock all of them. And the positions shouldn't change by much. If they're in the right position, you should be able to unlock them all. They shouldn't change, and they should sort of reach a stable state. So I just realized I'm doing it on the output file. Do that and that, and then we will save that. So it's 10851. So it improved again, not by much, but it did. And then let's check these. That's fine. That's fine. That's fine. That's okay. That's fine. This one changed a bit. And this one. But it's not changed by too much. So we can accept it. I'm gonna open Vesta and we'll see what it looks like on Vesta. Okay, so I've opened this file on Vesta. Everything's looking fine. There's no bonds that are at weird angles or weird distances, so I'm happy with that. So now we can go back on the input file. Let's run it again. And then accept that. We can then remove all of these. And let's refine the heavy atoms thermal displacement. Okay, so that improved this a lot. Let's have a look, see what the outcome was. 1.7, that's okay. Yeah, so we'll accept that. Then we can find this D3. If they go to something really wild, then I would usually keep them at 1.6. Let's see. Yeah, that's okay. We'll accept that. Okay, so now let's look at the structure. There it is. I'm gonna get up the cloud. 1 second. Okay, so we have accepted the thermal displacement for these, and now since there's nothing else we can do, this is the final structure. I load the density map. You can see everything's in the correct place. There's no incorrect bonds or distances, and you can change how you view this with this. This two-part makes it a bit more thicker, so it lets you see where the heavy atoms would be. Let's increase it. So yeah, I hope you enjoyed this tutorial, and it made it not too difficult for people that are using Topaz. And I'll make some more videos on some different crystals in the future. Thanks for watching. Okay, so as a final check, I let everything refine once again, and if we go to refine, we get a final RWP of 9.742. So we can then go and check all of the output files, and everything seems to look okay. There's no positions that are too far away from realism. The unit cell is okay. The thermal displacements are okay. So we can accept this, and if we then go to Vesta, we can then open recent, and here is the final structure.